The invisible race, mastering algorithmic time complexity in real-time systems in the world of high-performance computing, where milliseconds can determine success or failure. Understanding algorithm efficiency isn't just beneficial, it's essential. This exploration delves deep into time complexity analysis, performance profiling techniques, and practical optimization strategies that every serious developer must grasp. As we navigate through increasingly complex systems, from real-time financial trading platforms to autonomous vehicle control algorithms, the need for precise computational efficiency becomes paramount. These scenarios demand not just working code but code that performs flawlessly under extreme conditions. The Big O notation conundrum. Big O notation forms the foundation of algorithm analysis, yet its nuances often remain misunderstood even among experienced developers. It represents an upper bound on running time rather than exact measurements, which has profound implications when evaluating system scalability. This asymptotic analysis helps predict how an algorithm will behave as input size grows exponentially. However, relying solely on theoretical bounds can sometimes lead to suboptimal choices when dealing with practical implementation constraints. Common misconceptions include: Big O describes actual runtime instead of growth rate patterns. All O(n) algorithms perform equally well regardless of constants involved. Avoiding certain operations automatically guarantees optimal efficiency. The reality is that while Big O provides crucial information about scalability, constant factors and lower-order terms play significant roles in real-world applications. A careful balance between theoretical analysis and empirical testing proves necessary. Time complexity versus practical performance. While Big O gives us theoretical insights, real-world execution involves numerous variables that affect performance beyond pure algorithmic complexity. Memory access patterns, cache behavior, and hardware characteristics significantly influence actual runtime. An algorithm with better theoretical complexity might outperform a simpler approach due to these hidden factors. For instance, O(n) log n sorting algorithms may run faster than O(n) solutions when operating on small datasets due to smaller constant factors. Understanding the relationship between algorithm theory and practical implementation requires analyzing both worst-case and average-case scenarios. Often overlooked are amortized analyses that provide more realistic expectations. Consider these examples. O(1) array indexing is typically faster than O log n. Tree lookups in practice. O(n) superscript 2. Nested loops can be optimized using spatial partitioning techniques. Caching mechanisms dramatically change perceived time complexity in many situations. Profiling techniques for algorithm optimization. Effective optimization begins with accurate profiling. Modern development environments offer sophisticated tools ranging from basic timing functions to full-fledged performance analyzers that track memory usage and CPU cycles. Instrumentation-based profiling allows developers to measure execution times at granular levels. This method inserts measurement points within the codebase to collect precise timing data during operation. Sampling profilers take periodic snapshots of program state without modifying source code. They're particularly useful for identifying hotspots that consume disproportionate processing resources. Hybrid approaches combine both instrumentation and sampling methods to balance accuracy with overhead considerations. Choosing the right tool depends on specific use cases and available infrastructure capabilities. Best practices include: profile different inputs to understand variability in performance. Isolate individual components before analyzing interactions. Use statistical significance tests when comparing alternatives. Deterministic versus non-deterministic algorithms. Deterministic algorithms follow predictable execution paths given identical inputs. Their consistent behavior makes them easier to analyze and optimize compared to non-deterministic counterparts. Non-deterministic algorithms introduce randomness or external dependencies that alter execution outcomes. While they offer advantages in certain problem domains, their unpredictable nature complicates efficiency analysis. Examples of deterministic algorithms: bubble sort and quicksort implementations. Dijkstra's shortest path algorithm. Variations. Various machine learning model training procedures. Non-deterministic examples include Monte Carlo simulations, genetic algorithms for optimization problems, randomized quick select variants. Evaluating non-deterministic algorithms requires special consideration. Instead of focusing purely on worst-case scenarios, probabilistic analysis offers deeper insights into expected performance behaviors. The impact of data structures on algorithm efficiency. Data structures form the backbone of efficient algorithm design. The choice of structure directly influences time and space complexities across various operations. Hash tables enable O(1) average case lookup times, making them ideal for dictionary operations. In contrast, balanced binary search trees offer logarithmic time complexity for insertion, deletion, and retrieval tasks. Selecting the appropriate data structure often hinges on trade-offs between different aspects of performance. Some structures excel at particular operations while lagging in others. Comparative metrics: array versus linked list for random access tree versus hash table for prefix matching, heap versus sorted array for priority queue operations. Choosing between options requires considering both theoretical properties and practical application requirements. Empirical benchmarks help validate structural decisions against real-world workloads. Space complexity considerations: while time complexity receives most attention, space complexity plays a critical role in determining overall algorithm effectiveness. Efficient memory management prevents unnecessary resource consumption and avoids excessive garbage collection pauses. Some algorithms exhibit poor space complexity despite good time performance characteristics. For example, recursive implementations often suffer from stack overflow issues with large inputs. Optimization strategies for memory usage: implement iterative versions instead of recursive ones whenever possible. Reuse existing memory buffers wherever feasible. Utilize bitwise operations to reduce storage requirements. Memory locality also affects performance indirectly by influencing cache utilization patterns. Optimizing for spatial locality improves cache hit rates and reduces latency costs. Amortization analysis for complex operations: amortization analysis provides a more nuanced view of algorithm efficiency by averaging costs over sequences of operations rather than focusing solely on individual steps. This technique reveals potential optimizations where expensive operations occur infrequently amidst cheaper ones. Classic examples include dynamic arrays expanding capacity and disjoint set union find operations. Key principles behind amortization: total cost divided by number of operations yields effective average cost. Sometimes called pay-as-you-go pricing models, helps identify when upfront investment pays off long-term. Understanding amortized complexity enables more informed design choices regarding data structures and algorithm selection. It often leads to more efficient implementations than strict worst-case analyses would suggest. Real-time system constraints and trade-offs in embedded systems and other hard real-time applications. Meeting deadlines takes precedence over absolute optimality. This introduces new dimensions to algorithm evaluation criteria. Hard real-time systems require guaranteed response times under all circumstances. Soft real-time systems allow occasional delays but maintain acceptable quality of service levels. Designing algorithms for real-time environments involves balancing correctness with timeliness. Sometimes less than optimal. Algorithms prove preferable if they ensure predictable execution durations. Performance trade-off considerations: predictability versus computational intensity, error tolerance versus precision requirements, resource allocation across competing processes. Evaluation frameworks for real-time systems incorporate additional metrics such as jitter, determinism, and deadline miss probabilities. Specialized benchmarking methodologies are required to capture these unique characteristics accurately. Concurrency and parallelism challenges: modern processors feature multi-core architectures that necessitate rethinking traditional single-threaded approaches. Effective parallelism requires careful consideration of synchronization overheads. Dividing computations among threads introduces communication costs that can offset potential gains. Careful task decomposition ensures that parallel regions achieve sufficient granularity to justify concurrency efforts. Fundamental challenges include race conditions leading to inconsistent results, livelock and deadlock situations, contention for shared resources causing bottlenecks, efficiently utilizing multiple cores demands more than mere division of labor. Proper coordination mechanisms and load balancing strategies become essential components of any scalable solution. Best practices for concurrent programming. Minimize shared state to reduce contention. Use lock-free data structures where applicable. Employ fine-grained locking strategies. Judiciously measuring true speedup requires isolating pure computation phases from I/O bound activities. Careful experimentation validates whether parallelization actually improves throughput. Empirical benchmarking methodologies. Accurate performance assessment requires rigorous benchmarking that accounts for various environmental factors affecting measured results. Well-designed experiments yield reliable conclusions about relative algorithm efficiencies. Controlled testing environments isolate the subject under investigation from confounding variables. Multiple runs produce statistical samples enabling confidence interval estimation around key metrics. Important benchmarking guidelines. Warm up the JVM or interpreter before taking measurements. Run tests on representative hardware configurations. Use statistically valid sample sizes for each test condition. Automated benchmarking frameworks streamline comparative studies between different implementations. Regression testing suites detect performance regressions early in development cycles. Analysis best practices. Look for outliers in raw data before calculating averages. Visualize distributions rather than relying solely on numerical summaries. Report confidence intervals alongside mean values. Case study. Sorting algorithm comparison. Sorting presents an excellent opportunity to study algorithm efficiency differences. Different approaches vary widely in their time-space trade-offs depending on the situation. Let's compare three popular sorting techniques: insertion sort, quicksort, and merge sort. Each demonstrates distinct characteristics related to time complexity and practical performance. Insertion sort excels with nearly sorted inputs thanks to its adaptive property but degrades rapidly with arbitrary permutations. Its O(n superscript 2) worst-case scenario limits applicability to small datasets only. Quicksort boasts impressive average case performance with O(n log n) time complexity. However, its worst-case behavior remains quadratic unless carefully implemented with randomized pivot selection. Merge sort guarantees stable O(n log n) performance across all inputs but incurs higher memory overheads due to its divide-and-conquer strategy requiring auxiliary storage. Testing these implementations on varying dataset sizes provides concrete insight into their respective strengths and weaknesses. Comparative graphs reveal clear trends in performance patterns. Practical observations show insertion sort beats quicksort for very small arrays. Quicksort generally outperforms merge sort except in specific edge cases. Merge sort maintains consistency but uses more memory. Emerging trends in algorithm optimization. Advancements in hardware architecture continue shaping algorithm design paradigms. New technologies present opportunities and challenges that redefine efficiency standards. Quantum computing promises exponential speedups for select classes of problems. But realizing this potential requires developing fundamentally different algorithmic approaches tailored to quantum mechanics. Current research focuses on quantum algorithms for factorization and database searching, neuromorphic computing inspired by biological neural networks, heterogeneous computing combining CPUs, GPUs, and FPGAs. Machine learning techniques themselves pose interesting questions about algorithm efficiency. Training deep neural networks involves massive computational demands that challenge traditional optimization approaches. These emerging areas emphasize the need for continuous education and adaptation. Staying current with technological developments ensures that our understanding of algorithm efficiency evolves appropriately. Future directions for researchers include developing new mathematical models for unconventional computing devices, improving energy efficiency in distributed computing environments, creating hybrid classical quantum algorithms for intermediate-scale problems. Conclusion: mastering algorithm efficiency goes beyond memorizing time complexity formulas. It requires understanding how theoretical analyses translate into real-world performance across diverse application contexts. By combining analytical techniques with empirical validation, developers gain the ability to make informed trade-offs between different algorithmic approaches. This knowledge empowers creation of software that meets functional requirements while maintaining exceptional performance characteristics. Remember, the goal is always to create the most effective solution, not necessarily the fastest one.